Hi everyone, good evening and welcome. Thank you for joining the session. So today I'll be talking about stable matching. So what is a stable matching? What is a matching? Okay, to motivate the problem, let's look at something like this. There are some applicants who are applying to some colleges. So every applicant has a preference list. So let's say this is applicant A, and maybe maybe they like college one the most, and then they like college two. College two is the second preference, and so on. So, and then similarly, every college also has a preference list for every applicant. So maybe based on the applications that they got, they decided that okay, let's say college one decided that they like applicant one the most, and then they prefer applicant two, and so on. Some arbitrary permutation, and this is the same for every college. So the setup of the problem is like this, where you're given, let's say, n applicants and n colleges. So what we want to do is, and further we are also given for every applicant, there's some preference list for the college, of the colleges, and for every college there's a preference list of all the applicants. This is the setup of the problem. And what do we need to do? Let's say for now we just want one applicant and one college paired up together, so that like exactly one applicant and exactly one college, they should be matched together so that uh, some nice condition is satisfied. Okay, and like the same, yeah. So what is the nice condition? You will say that, let's say, okay, and then similarly we can also say this about like to make it even more nicer, and like to make the terminology better. I'm just going to look at men and women. So let's say you're given n men and n women. Each man has a preference list of all the women. Each woman has a preference list of all the men. And what you want to do is pair up one man and one woman so that there's no instability as such. So, what is an instability? Basically, let's say there's this man M1. There is no man basically who is paired with W1 currently, let's say. And let's say M2 is paired with W2. Now we say that M1 comma W2 is an instability if M1 likes W2 more than W1, and the W2 also likes M1 more than W2. So that is an instability. Is the definition of an instability clear? Or okay, is the setup of the problem clear?
Yes. Yes.
Oh, awesome. Thanks. Yeah. So this is what you wish to do. Okay. Any questions so far? Okay, awesome. Yeah. So any ideas about? Okay. So what are the questions that we can ask here? First of all, will like okay, let me ask one question that is coming to my mind. Will every instance have a stable matching? So this is how I'm defining a stable matching, where there are no instabilities, and each man is paired with exactly one woman, and each woman is paired with exactly one man. So, yeah, will every instance have a stable matching? For example, what do you think? So, we try to come up with an instance where there is no stable matching. Should be easy, right? Okay. So, maybe we can keep this as a question for later on. Let me just write this out. It's okay. Does every instance contain a stable maximum? All right. Okay. And another question I really want to ask here is, if an instance does have a stable matching, how can we find it? So any ideas about that? Okay, let's think about it for a while. Um, Maybe let's just consider a pretty naive way to do this. Okay, yeah, any thoughts about the first question? Do you think just a yes or no question. Do you think every instance contains a stable matching? Um, okay, I'm not sure if this is an issue, but I would really encourage you to just unmute and talk. But it's just a simple yes or no question. Is the question clear?
Yes.
Okay, awesome. Thanks. So what do you think? Does every instance contain a stable matching or no?
I mean, it would be like really cool if the answer is yes, but I don't know what the answer is.
That is true. It would be really cool if the answer was yes. Do you perhaps have an idea in mind for how something with no stable matching would look like? Maybe we can try it and work it out. How do you think an instance with no stable matchings would look like? Maybe if everyone had the same preference list, right? Then no matter how we paired people up, there would always be an instability. That sounds pretty intuitive, right? Let's say like we have three people here, three people here. Mm, let's call these M1, M2, M3, and these are W1, W2, W3. So let's just come up with, let's say everybody likes W1 the most, and then W2, and then W3. And similarly, everybody here, let's say, likes M3 the most, and then M1, and then M2. So, can we try to come up with a stable matching in this case? Does there exist a stable matching in this case? So, let's say we pair M1 with W2. We pair M3 with W1 and M2 with W3. Is this a stable matching? So M3 and W1 don't want to change clearly. M1 uh, doesn't, M1 likes W2 better than W3. So M1 doesn't want to change. And yeah, so there's nothing that we can do really. Like M2 likes W2 better, but W2 doesn't like M2 better. W2 likes M2 the worst. So this is a stable matching. There are no instabilities. Does that make sense? I hope this helped in clarifying. Yeah. Go ahead. What
But
do you think?
if we take M2 and W3, so M2 likes W1 better, for example, and W3 likes M1 better. Is so this is like an unstable matching, right?
Good question. So over here, an instability is just one man and one woman who are not paired currently. So what are you saying is an instability?
M2 and W3.
Okay, no. So M2 and W3 are currently paired. So that is not an instability. An instability would be maybe M2 and W1. Ideally, they should be paired. So let me repeat the definition of instability. This was an excellent question. So we say that M1 and W2 are an instability if they're not paired in our matching, and but they should be paired. Like M1 also likes W2 better than his current partner, and W2 likes M1 better than her current partner. So अगर मियाँ बीबी राजी तो क्या करें? I forgot the exact quote, but yeah. So they should be paired. So over here, an instability would be some man and some woman who are not paired, but they should be paired. Does that make sense?
Yeah, so because like their preferenceable matches are like already used up, we can say that's why it's not an unstable match.
Kinda. So let's just see an example. Why is M2, W1 not an instability? So they are not paired, but and M2 likes W1 more than his current partner, but W1 is currently paired with M3. So W1 doesn't want to change. Even if M2 wants to switch to W1, W1 is happy with her current partner.
Yeah,
So
makes
this
sense.
is not an instability,
Yeah, makes sense.
right? Okay.
Yeah.
Awesome. Okay, thanks. Any other questions? Okay, awesome. So we can move on. So, okay, this contained a stable matching. So hopefully we're clear on what an instability is, what a stable matching is. Uh, Moving on. Okay, did somebody want to say something? Okay. Let's consider a pretty naive approach to finding a stable matching, right? How do we go about finding a stable matching? Let's say it's something. Okay, here's what you will do. Each man will. And okay, just before we move on, something I should clarify is this is a very special case example where all the men had the same preference list and all the women had the same preference list. But this may not always happen. For example, M2 might like W3 the best, and then W1 and then W2. So this could also be an instance, and so on. So yeah. Now let's say here's what you'll do. Here's what you'll make them do. First, you will say that every man we choose some man, let's say M, uh, and he'll ask M and go and propose. In I'm doing air quotes. So propose to the highest ranked person in his list who has not yet been proposed to by M. So let's say M has not yet proposed to W, who is the highest ranked person in M's list, who has M. So initially, M hasn't proposed to anyone, so M will just go and propose to his first preference. And yeah, so now every time a woman is proposed to, she will either accept or reject. So when will she accept? If she has no partner, if she's not engaged with anybody, she'll accept. Otherwise, she'll decide, okay, let's say her current partner is M prime and M just proposed to W. Then what W will say is, W will see, does she like M prime more than M? In that case, she'll just be paired with M prime. If she likes M more than M prime, then she'll say bye bye to M prime and get paired with M. Does this make sense? So what you're doing is, each man goes and proposes to a woman who is ranked high in their list, And if that woman is not paired with anybody, she might as well get engaged with this man because, yeah. And then if she is currently paired with somebody, let's say M prime, then she'll decide on who she likes better. Like which can be decided by the preference list, right? So if she likes M prime better, she'll reject M. So M has to go and propose to somebody else. And otherwise, she'll reject M prime and get together with M. So M prime now becomes what I will call free. So M prime is not engaged to anybody. So M prime will become free. So this is what we are going to do. And when does this algorithm, yeah, this is what we are going to do. So we keep on doing this for an indefinite amount of time. So let me just write it down for the sake of clarity. So this is something that is called a pseudocode of an algorithm. So if you've not heard of this before, usually people, what we do is, a pseudocode is something that is not in any programming language. So if you might have heard of Python, Java, C, and languages like that where people do the actual coding. And here, if you just want to study the code and not actually write it down in Python or Java or whatever, you can just write a pseudocode. So the pseudocode for this is, while there is a free man, let's say M, what we do is uh, M proposes to the highest preference, let's say W, who he hasn't proposed to yet, And then if W is free, then W is engaged to M. Otherwise, say W is paired with, or let's say W is engaged to M prime, then we decide if W likes M prime better than M, then W rejects M, so M is still free. Otherwise, it means that W likes M better than M prime. So else M and W are engaged and M prime is now free, right? So this is what the algorithm is doing. Okay, any questions about this? Okay, awesome. I have a question about this. What happens, like, if this algorithm just never ends, it just goes on forever? Can that happen? Okay. Yeah, I hope the algorithm is clear. So the question that we'll try to answer is now, does the algorithm terminate, right?
Probably the answer is same as whether a stable matching exists in like every instance or not.
I see. Very interesting. So I think correct me if I'm wrong, but what Anya is trying to say is it will terminate if there exists a stable matching. Otherwise, it will go on forever. Right? Okay, interesting. Well, as it turns out, okay, so tell me this. How many proposals can a man make in the worst case scenario? Okay, maybe not ask that question. Let's not ask this question yet. So, what is the condition for this algorithm to run forever? In what condition? So, let's look at this. This algorithm runs while there is a free man M. So, when does it stop?
When there is no free M.
Exactly, when all the men are engaged with somebody. So, when will it go on forever? When there's a man who is not getting engaged to anybody, everybody just keeps on rejecting him, right? So can that happen? Let's say the algorithm, uh, say the algorithm is not ending. What does this mean? This means that there is a free man. What does that tell us? Can all the women be engaged to somebody?
No. Like
No.
it's in the is there.
Exactly. I mean, throughout the course of the algorithm, every man is paired with exactly one woman, or at most one woman, right? No man is paired with two women at any point in the algorithm. So this means that there's a free man, which implies that there must be a free woman as well, right? Does this make sense?
Yeah.
Okay, awesome. So, okay, now can you sort of try to finish the argument from here? So
So
M,
they will
yeah,
be like necessarily paired up with each other because the woman who's free does not have any other option but to get engaged with that person.
exactly, awesome, great. So M has to have proposed to, okay, let's call this free man M and let's call this free woman W. Then M uh must have, okay, 1 second. How do I yeah. M must have M must propose to W at some point, right? Because he is free. So, and what does this mean? This means that uh, W has to accept simply because of how the algorithm works, right? If W is free, then W has to get engaged to M. And after that, so M will get engaged to somebody and then the algorithm will end. Make sense?
But what if like M this M proposes to somebody else and then that woman accepts the proposal and so the other man becomes free and that other man who is now free he proposes to some other woman who is like already engaged and then that woman accepts the proposal and what if this goes on forever, right? Can this happen?
That's a very good question. So let's try to look at it more carefully. Um, so the more important part of this is M only proposes to somebody he hasn't proposed to yet. Which means M doesn't propose to the same person twice, right? So let's say at the end of the algorithm, there's a man who's not paired with anybody. Then there's a woman who's not paired with anybody. But since M is not paired with anybody at the end of the algorithm, it must mean that he has proposed to everybody already. Otherwise, if let's say, right, okay, even more precise argument would be M must have proposed to W at some point because yeah, because M is currently not paired with anybody. Does that make sense?
Okay, right. So,
So
like we are
the
not
main point
considering
to
the
what,
case.
yeah.
So we're not considering the case where M has never proposed to anybody and he's just free because he's not proposed. Or probably he proposed to some people and then he stopped proposing after that because he could not make a match with anybody.
Yeah, that's what happened. That's why M is free. M is free because he proposed to everybody and nobody took him in. But that doesn't make sense, because if M is free, then there should be a woman who is free. And if M proposed to that woman, then they must have been engaged. So that's a
Yeah.
contradiction.
Right.
Okay, awesome. So what does that tell us? This is a contradiction, right? This means that the algorithm always ends, right? Does this make sense? Does this argument make sense? Okay.
Yes.
Oh, awesome. Thanks for Twitch. Uh, yeah. Okay, what can we do next? Well, the next question to ask is, we know that the algorithm ends, but does it give us a stable matching? Uh, does the algorithm give us a stable matching? Okay, let's say it does. Let's say we somehow prove that it gives us a stable matching. That would be very cool, as Anya was talking about earlier, because that would mean that every instance has a stable matching. No matter what we change the preference list to, we will always have some stable matching. So this is what we are going to do. We are going to try and prove that whatever the matching outputted by the algorithm is, it's stable. So how do we go about doing this? So let's just assume, for the sake of contradiction, uh, let's assume that it doesn't give us a stable matching. Right? What does that tell us? There must be an instability. Let's call that instability M and W. Okay, let me clarify what I mean by this. It means that M and W should be paired up together, but they aren't paired up together. Which means that M likes W more than his current partner, and W likes M more than her current partner, right? So let's try to see how that looks like. Let's say this is M, and let's say M is paired with W prime currently, by in the output of the algorithm. And let's say this is M prime, who is paired with W in the output of the algorithm. And we're saying that M comma W is an instability, which means M likes W more than he likes W prime. So in the preference list of M, W comes to the left of W prime. And similarly, W likes M more than current partner, which is M, right? So before we proceed to the rest of the proof, I'm just going to state a small observation and see if it makes sense. Okay, what happens during the course of the algorithm? What happens to the partner? Let's say W is currently, let's say initially, let's say a woman W was paired with M. And then W later on went and rejected M. So W got paired with, let's say, somebody else, and so on. So this tells me something nice. So throughout the algorithm, the partner of a woman the partners of a woman keep getting better. Let's see if this statement makes sense, right? So why is this happening? Let's say, yeah, please go ahead.
Yeah, it does make sense.
Right, can you give a quick explanation for why this is happening?
Because W will only reject like her current partner only if she gets proposed by a better person, and like if the reverse case happens, then that will not take place.
Exactly. I couldn't have said it better myself. So W only rejects somebody if she likes that her new proposal better. So if W does change partners, then they only keep on getting better and better. Okay, so we're going to use this observation. Now, okay, let's look at this preferences. We know that M likes W more than W prime. What does this tell us? This tells us that M must have proposed to W before he proposed to W prime, right? Simply because of how our algorithm works. We're saying, so M proposes to the highest preference, but he hasn't proposed yet. Which means M will always propose to somebody more preferred before he proposes to somebody down in his list. So M must have proposed to W at some point, right? Before he proposed to W prime, right? So let's write that down. M, okay, must have proposed to W before he proposed to W prime, right? Why is that? I'll just give a quick explanation again. Because M proposed W more than W prime. Why is that? Because we're assuming, for the sake of argumentation, that M and W is an instability. That means M likes W more than his current partner and W likes M more than her current partner. So we have this. Right. So what happened then? Can somebody try to finish the proof from here? So in the end, let me give you more hint. In the end, M is not paired with W. Which means W must have rejected M at some point in the algorithm. Right? Let's write that down. W must have rejected M at some point in the algorithm. Okay. Can you try to finish the proof from there? Oh, also hint, we have this observation from earlier. The partners of a woman cannot get worse.
Are we assuming that M and M prime are the only men, or are there more men and we're just not taking
Yeah,
that?
there could be more men and more women, but we're not really concerned about them for now.
No, but like if there are like more men, and for example, say M double prime is also a man, which is like earlier in the preference list of W than M. So she might have like rejected M's proposal because she was getting a proposal from M double prime. So I don't know.
Okay, awesome. I like where this is going. So, W must, and then let's say W rejected M because of some M double prime who she likes more than M. So what happened? W was paired with M double prime, right? But then what happened at the end of the algorithm? W is paired with M prime. Can that happen? So at some point in the algorithm, W is paired with M double prime. But at the end, she is paired with M prime. Why can this not happen?
Yeah, because she will like not accept the proposal. Right.
Exactly. Because of this observation, that partnership of women cannot get worse if we can only keep on getting better. So it must mean that that's a contradiction, right? At the end, she is paired with M prime, which she likes worse than M double prime. This contradicts the above observation. Right? Does this make sense to everyone? Okay, awesome. If you have any questions, now is a good time to ask. Okay, awesome. Glad to know everybody's understood. Okay, another nice question to ask here is what does like the we haven't said that which we haven't mentioned which man we choose. We're just saying while there is some free man M, we choose him. We haven't mentioned an order for the men, right? Like maybe we chose M1 first, M2 later, or we chose M2 first, M1 later, right? So yeah, can it happen with choosing like M1 first and M2 later, and M2 first, M1 later? It gives us the same matching. Can that happen? What do you think? So let's write down this question. Does the order in which the men are chosen matter? I.e., do they give us different stable match? Also, can it happen that they give us the same stable matching? Is the question clear? Okay. I will take the silence as a yes. So, any guesses for, or you can also say, okay, you can say that you think this will happen with high probability. If you don't want to be, if you don't want to sound sure, if you don't want to make a guess, you can say things like that. What do you think is more likely to happen? Okay, so at least when I saw this first time, I was like, I mean, clearly, if we make M1 propose first and M2 propose the last, it's going to give us a different stable matching than when we make M2 propose first and M1 propose last, right? I mean, there's no reason for them to give the same stable matching. Maybe if M1 proposes first, he gets his first preference, and then if M2 proposes first, he gets his first preference. And that would be different stable matches. But as it turns out, it's really cool and very mind blowing. At least for me, that every run, no matter the order of the men we consider, we will always get the same stable match. And the coolness doesn't stop there. Right. So over here we had an observation that throughout the algorithm, the partners of a woman cannot get worse. They, if anything, they only keep getting better. Similarly, what can we say about the partners of each man?
They keep getting worse.
Exactly. Awesome. So, and similarly, the partners of a man keep getting worse. So we would expect that this algorithm is pretty biased, right? It seems to be doing pretty bad for the men and pretty good for the women, right? So we would expect that something like that. So can we like quantify this in a way? So can we define, let's say, best partner for a man and a best partner for a woman? So let's try to do that, and then you will prove the main theorem of this, which is the most mind blowing of them all. Oh, before we move on, I forgot to mention this. We showed that in any instance, the algorithm terminates, which means that given any instance, you will always have a stable matching. And we also showed that when the algorithm does terminate, we get a stable matching. So we've shown that every instance has a stable matching. And now what we're going to show is every run of the algorithm gives the same stable matching, and furthermore it is some particular stable matching which I will define right now. So
No, like how does the ending of the
I'm going to,
algorithm
yeah.
prove? How does the ending of the algorithm prove that it ends in a stable match?
Okay, so we proved this, right? We assumed for the sake of contradiction that it wasn't. Yeah, we not the ending. We still had to do some more work where we had to show that, yeah, we assumed that there it wasn't a stable matching, and then prove the contrary, right?
Yeah. Also, the last
Yeah,
question
yeah.
which you asked, like, does the order in which the
Mm-hmm.
man manages a man? I think the answer would be no, and the the reasoning can be drawn from the observation that the partners of the women keep getting better. So, irrespective of how the men are chosen, she will choose the best man who proposes to her.
Right. So what Anya is saying, in a way, every woman will kind of get what is best for her, right? Is that what you're saying?
Yeah.
Okay, I like that. So let's try to quantify more. What you will say is, okay, I'm going to define a set, which I'll call a valid partner. Okay, let me make this bigger. So I'll call this is going to be a set. Let's say a valid partner of M is the set of all women, or W, so that, so this is just fancy notation for sets. If you don't know it, it's all right. Is the set of all women. So given a man, I'm going to define valid partner of M to be a set of all women, so that there is a stable matching. There is a stable matching where M and W are paired. Right? This is how I'm defining the set of all valid partners of M. Okay, is this definition clear? This is very important to what we're going to do after this. So, for example, there could, let's say for a man M1, there could be a woman W1, let's say, so that there is absolutely no hope for M1 and W1 to be together. They cannot ever form a stable. There cannot be any stable matching with M1 and W1 to be together. So W1 will not be a valid partner of M1. But let's say there is a stable matching where M1 and W3 are paired. So W3 will be a valid partner of M1. Make sense? Okay, I'll take the silence as a yes. And similarly, this is not only for men. This is also, we can also similarly define this for a woman. So a valid partner of woman, this is just the set of all men for which we can pair it up. For there is hope in, if you want to say it in a more intuitive way. Okay, I hope this made sense. Now, okay, I'll ask you. This is again pretty intuitive. How will I define a best valid partner of a man? Let's say this is pretty intuitive, so you can give it a shot. Yeah, it's like exactly what it says. So a best valid partner of M is just uh, a valid partner of M who M likes the most among all the women. So among it is just it is a single woman. So valid partner of M was a set. So the best valid partner is just out of all these women who are valid partners of M, who does M like the most, right? That is what it is. Uh, Does that make sense? I hope that makes sense. It's pretty intuitive. And similarly, we can also define the worst valid partner of a man, which is just the woman he likes the worst among all of these valid partners. It could also happen that maybe the only valid partner for M is like only one woman. Then in that case, the best valid partner and the worst valid partner for M are the same person. Who's that woman? Who is the valid partner? Right? So yeah. So what Anya said, and it is pretty intuitive, that the woman will be paired with her best valid partner, right? Or like in a way, maybe we can wishful thinking. Like it would make sense for that to happen, right?
I have a question.
But yeah.
What do you exactly mean by the order in which the men are chosen?
Okay. So over here, like let's say we have so many women, right? We could choose any to go to this next step. So does it matter which one we choose first? That is the question.
Your voice was not very clear to me.
Did that?
Can you repeat that?
Oh, yeah, yeah. I think it was a connection from my mind, which will be clear now. The question, it just means that we could have multiple free men, right?
Yeah.
So which one do we choose to like do this next step? Which man do we choose? Does it matter which one we choose first, which one we choose second, and which one we choose
Yeah. Right.
third, and so on? That's the question. Yeah. Uh, okay. So like Anya made some brilliant conjectures, but like what I'm going to do is just sorry, Anya, your conjecture was wrong. And that is what I did when I first learned about it. I was like, it seems pretty intuitive because a woman's partner, they only keep getting better, so it makes sense for her to be paired with somebody's like pretty good for her. But I was like mind blown when I learned that this is not the case. Actually, every woman, the thing that is outputted by the matching that is outputted by the Gale-Shapely algorithm actually pairs every man with his best partner and every woman with her worst valid partner, which is extremely non-intuitive, right? So let that sink in. And yes, you have trust issues now. So how do we go about proving this? Again, okay, maybe I should just pause for like 10-15 seconds here.
No, but are they not like two different questions about whether the partners of like the first group get better or the second group better, and does the order in which the men are chosen matter? I think they're separate questions.
Oh, yeah, that's another good question. So let me clarify. So, what I'm saying is, Gale-Shapely, no matter what order you take, always outputs this stable matching, this particular stable matching, always, which is pairing up a man with his best partner and pairing up a woman with her worst partner, worst valid partner and best valid partner. Did that make more sense, Anya?
Yeah.
Okay, right. So, yeah, we can. How do we go about proving this? So, I'll only do. I'll only prove the best valid partner part and the worst valid partner for every woman. That can be shown in a very similar manner. So, how does the proof go? Again, we'll assume for the sake of contradiction that there is a man uh, who isn't paired with his best valid partner, right? Note that the best valid partner of M is not necessarily M's first preference. I said this again, I said this before, but I will say it again because it can be confusing. So, the best valid partner for M is not necessarily his first preference because maybe it happens that there is no stable matching with M paired with his first preference, right? So, yeah, I just wanted to make that clear. Okay, so for the sake of contradiction, that this a man who's in pair with his best valid partner. Now, I'm going to assume something very strong. Consider the first time in the algorithm when a man was rejected by his by a valid partner. Okay, let's see if this statement makes sense. Does this make sense? Say a man W, a man M was rejected by a valid partner W. This is the first time in the entire algorithm. Let M have the honor of getting rejected, being the first man to get rejected by a valid partner. So a lot of rejections were happening so far, but they were of non-valid partners. But then this is the first time in the algorithm that somebody has gotten rejected by their valid partner. Right? Okay, now it's a very easy claim. Now I claim that W must be M's best valid. Why is this true? Can somebody give a quick argument? It's pretty straightforward. So if you're not getting it, you're probably overthinking it. So since this is the first time when anybody was rejected by their valid partner, so let's say W is not M's best valid partner, which means M must have been rejected So why did M propose to W in the first place? Because he was rejected by someone who he liked more than W. That means M must have been rejected by his best valid partner as well at some point. But then we're saying this is the first time in the algorithm when anybody was rejected by their valid partner. Does that make sense? Which is a contradiction. So W must be M's best valid partner. Did that make sense? And maybe I'll just say it in a nicer way. Let's say W prime is M's best valid partner. Then M must have, and since W is a valid partner, but W is not M's best valid partner, M must like W prime more than he likes W. Which means M must have proposed to W prime at some point. But W prime must have rejected M, which contradicts this. Then the first instance would have been M and W prime, right? It wouldn't have been M and W. So this means that W has to be M's best valid partner. Does that make sense? This is just the start of the algorithm, start of the proof.
Yes.
Okay, awesome. Thanks. Right. Now let's just try to draw some things. So let's say at the end of the at the end of the algorithm, M is paired with some W prime and W is paired with some M prime. Again, a very similar argument to what we have done earlier. So clearly M and W aren't paired together because W rejected M. So M will never propose to W ever again. So they can't be a pair at the end. So M is paired with somebody, say W prime, and W is paired with somebody, say M prime. Now, since W is M's best valid partner, or she's a valid partner of M, which means there exists some stable matching, some other stable matching in which M and W are paired together, right? Does that make sense? Okay, so what I'm going to do now is just write down this. So since there are no instabilities here, okay, first of all, we know that since M was rejected by W, it means M likes, and then later on went on to pair with W prime. M must like W more than W prime, right? Because the partners of a man only keep on getting worse, and we know M was rejected by W, so M must like W more than W prime, and we also know that W must like M prime more than more than M. Again, because of the observation that the partners of women can only keep on getting better. Now, okay, is this clear so far?
Yes.
Okay, awesome. Now let's consider this other stable matching in which M and W are actually a pair. Why does this stable matching exist? Simply because W is a valid partner of M, and that is exactly how we define valid partners, right? We define valid partners of M to be some person who is a set, but yeah, a valid partner of M, so there should be a stable matching in which these people are paired. So there is a stable matching, let's call it S, in which M and W are paired. So who is M prime paired with? Let's say M prime is paired with somebody. W double prime. Now, what do we know? We know W likes M prime more than M. So in this stable matching S, can M prime like W more than W double prime? What happens if M prime likes W more than W double prime? We know that W wants to be with M prime more than M because of this, right? So W likes M prime more than she likes M. Now if M prime also likes W more than W double prime, what does that tell us about M prime and W? Is the notation confusing? Should I name it or something else? Or so maybe I should just say it again. We know that W wants to be with M prime more than M. What happens if M prime wants to be with W more than his current partner? Then this will be an instability, right? Because W also likes M prime more than her current partner, and M prime also likes W more than his current partner, right? Does that make sense? Should I repeat? So if M prime liked W more than W double prime, it would mean that M prime comma W was an instability because both M prime and W want to be with each other more than their current partners. So it must mean that M prime likes W double prime more than W. Okay, so should I repeat once again? Okay, which part is not clear exactly? Please feel free to speak up. So yeah, maybe I can just say it one last time. It's like pretty easy to see. So we have M and W are paired in some other stable matching, right? And let's say in that stable matching, M prime is paired with W double prime. And we know because of, sorry about that, something happened. Yeah, we know that because of this, we already know that W likes M prime more. If M prime also like W more, then M prime comma W would be an instability. It would be a contradiction. So M prime must like uh, W more, W double prime more than W. So let's write them down. M prime likes W double prime more than he likes W. And that clearly gives us a contradiction. So why is that a contradiction? So because now note that W double prime is a valid partner of M prime. Why is W double prime a valid partner of M prime? Because there's a stable matching in which they are paired. So and W M prime likes W double prime more than W. So in this case, in Gale-Shapely, in the algorithm that we saw, M prime must have proposed to W double prime before he proposed to W and must have gotten rejected. which is sad because we give M the honors of of the person to be the first to be rejected by a valid partner. But then it turns out that M prime was actually rejected by his valid partner before M, which is a contradiction, right? Does that make sense? Okay. So it can be sort of hard to uh, understand, but yeah, it's a pretty straightforward argument. If you just write down the preference list and just try to contradict their assumption, it all works out very nicely. So yeah, this is a contradiction, which means that this was actually right. So every man is paired with the best possible partner that they can get, and every woman is paired with the worst possible partner that they can get. Okay, I haven't proved the woman part yet, but it is kind of similar to this. So I encourage you to try and prove it as an exercise. And if you're not able to do it, then feel free to contact me and we'll try to figure it out together. Okay, shall we move on? Uh, Awesome. So I will just take the silence as a yes. I hope that if you have any questions, you will just unmute and ask. Okay, so the last part of this is okay, I'll just state some nice results. One is about this. Can a man or a woman like submit a fake preference list and like hope to get a better partner? Okay, so the algorithm that we saw here just now, it's known as the Gale-Shapely algorithm because it was devised by two computer scientists, Gale and Shapley. And yeah, let me maybe just do a quick recap of what all we saw. So first we looked at the problem. We defined the problem properly, where every man has a preference list, every woman has a preference list. And then we looked at the algorithm or the pseudocode of the algorithm. And we tried to analyze the algorithm in terms of and what kind of a stable matching does it give us? So it gave us some very expected results. Another analysis that is typically done for algorithms is how long does it run for? So we don't want our algorithm to run too long and just be very slow because in today's world we have huge amounts of data in like yeah just huge amounts of data and that number is just going up, it's not going down. So we want our algorithm to be pretty fast in terms of the input. So how can we quantify this fastness? So what we can try to do is what happens in the worst case scenario. In the worst case scenario, every man proposes to every single woman, which means that man number one proposes to n women, man number two proposes to n women, and so on until the nth man proposes to n women, which means that in total, at most n squared proposals are made, right? No more than n squared proposals are made. So if there are n men and n women in the input, at most, like we say in a very rough terms, we say that we take at most n squared time. So this is also known as the runtime analysis of an algorithm. And sometimes we also do a space analysis. So how much space is it taking up on our computer? So over here, just to store all the preference lists, we are using n squared space. If we assume that, say, every number is, or every man and or a woman is takes up like one bit of space, then we're using n squared bits of space. So yeah, that was just the side note about analyzing runtime and space complexity. And then coming back to this particular algorithm. So yeah, as I was talking about, uh, another interesting result is even if a man or a woman submits a fake preference list, like maybe they have some actual preference list, but they submit something else in order to get a better, uh, in order to hope to get a better partner. Uh, the surprisingly, this cannot happen. Like even if you submit a fake preference list, you have no hope of getting a better partner than you originally got because of the Gale-Shapely algorithm, which I think is very interesting. And this is like same for man and woman. And I think yeah, as an exercise, maybe you can take it up and try to prove this. It's very similar to this. The idea is to essentially just again maybe try contradiction and try to look at preference list. This list of everything we know. So like we knew that M must like W better than W prime, and so on. And then somehow we arrive at a contradiction based on all of these preference lists. So yeah, that is essentially the idea. Another very interesting thing is there is no even an unstable matching. There is no stable or unstable matching in which a man is paired with a partner which is like every man is paired with a partner he prefers more than his best valid partner. So maybe I could just write this down. It's kind of complicated to say in the head. There is no matching, stable or unstable, in which every man is paired with someone better than their best valid partner. In short, what this is saying is there we cannot have any match. Then I think this is even more strong because we are talking about like we are allowing the matching to be unstable even in which every man is paired with somebody who's better than who they were paired with by the Gale-Shapely algorithm. And maybe we can also quickly look at the proof. So let's look at all the men. M1, uh, M2 up till Mn. And let's say we have the, let's say the stable matching outputted by the Gale-Shapely algorithm has, let's say, let's call it S, in which we are paired with, in which there is some pairing, and then let's assume for the sake of contradiction that there is some pairing in which every man is paired with somebody better, who he likes more than less. And now we will try to come up with a contradiction. How will we do that? So a nice observation. In the Gale-Shapely algorithm, the woman who gets matched last, who gets paired last, does not reject anybody. Right? Does that make sense? Let's write this observation down. In the algorithm, the woman who is paired last does not reject anyone. Yeah, does somebody want to say something? Okay. Uh, okay, does this statement make sense? Does this observation make sense?
Yeah.
Okay, awesome. Uh, Now let's just say that W is a woman W is the woman who was matched last in the GS algorithm. So does that tell us anything? And let's say that uh, W is like paired with M1 in the algorithm, which is in the matching, which is human for contradiction, does better for every single man. It's like a pretty straightforward argument. Let's say the Gale-Shapely algorithm paired the M1 with, let's say, W prime, but there is a better matching which could be unstable, in which M1 is paired with W, which means M1 likes W strictly more than W prime. But then there's a contradiction, because M1 must have proposed to W at some point and W must have rejected M1. But that's a contradiction, because we just said that the woman who is paired last does not reject anyone. So the woman who is paired last, uh, like, she has to be paired with M. Did that make sense?
Yes.
Okay, awesome. Thanks. I think, yeah, and then maybe I can just end with some interesting exercises to think about, uh, and some nice results maybe, and some more questions to think about as well. So, one of the questions is, can we extend this algorithm to sort of colleges and applicants, where every college has a capacity of more than one applicant? So, first of all, we need to define that problem properly. So, we want, what would an instability be in that case? And in that case, can we sort of extend Gale-Shapely to find a stable matching with a college accepting more than one student? And uh, which is related to the thing that we did in the end, can we find an exercise could be to find an example uh, where there is an unstable matching in which some men get better partners than the Gale-Shapely's output, but no man gets worse in worse than the Gale-Shapley output. Another A few more nice problems to think about could be um, just, can we always have some person who is paired with their first preference in the output of Gale-Shapely matching? So can we come up with an example where an there's everybody's there is nobody who's paired with their first preference?
I don't think there can be a case where like everyone is paired with their first preference. Is that
Oh,
that's
I think that can easily happen. If every man has a distinct, different first preference,
oh
then they'll
okay,
all
yeah.
be paired with their first preference. I think the question I was trying to ask is, does Gale-Shapely always pair somebody with their first preference, or
Yeah, it always at least
can
one
there be an
person.
instance?
One person would at least have the first
Okay,
preference, right?
okay, so that's not true. So I spoiled the answer for you, but maybe you can try to prove that it's not true and come up with a counter example where every man is not paired with their first preference. Which is why this sort of is not obvious what we did at the end. Uh, and then I have like more questions. Like maybe we another nice example would be to construct an instance where somebody submits a false preference list and does not get a better partner, but some other person gets a better partner because of that. Maybe that can happen, or that cannot happen. Another interesting property is, let's say we have two stable matchings. This is not related to the Gale-Shapely algorithm, but it's a nice question nonetheless. And what we do is, let's say M1 is paired with somebody W1 in S, and M1 is paired with, let's say, W1 prime in S prime. Then we construct the third stable matching, let's say S star, in which M1 is paired with the person who he likes more in W1 and W1 prime. And this we do for every single man. Then a very interesting theorem is to show that what S star is indeed a proper matching, which means that no man is paired with two women and two same women, or no woman is paired with two same men. And further, that it is stable. And the same thing can be showed for the other way around as well, where we define S star to be, in S star we let M1 be paired with somebody, with the person he likes less in W1 and W1 prime. In that case also it cannot happen. It's very surprising, not at all obvious, that a woman is paired with two men or a man is paired with two women. And like even more than that, it's a stable matching. There are no instabilities. Yeah, so these were some of the cool things that I thought were pretty mind blowing when I learned all of this. I think this is more or less what I had in mind for today. Are there any questions or comments about any of this?
I'm so sorry I'm late today. There was a power shutdown today, and will you be taking more classes?
Sorry.
Will you be taking more classes?
Oh, I don't know. I'm not sure. Uh,
I hope so.
okay. Thanks. Thanks for joining. Yeah, we can stop the recording if there are no more questions.
Thank you for the class. It was quite wonderful.
Thank you all for joining. I had a lot of fun too.